Hello, this is Dan List, and today I'm going to be explaining how to do section 1310, problem number 11. As you can see here, I'm showing you the problem from the book. It says in exercises 11 through 14, use Lagrange multipliers to find the indicated extrema, assuming that x, y, and z are positive. And it gives us a function f of x, y, z equals x squared plus y squared plus z squared, and the constraint x plus y plus z minus 9 equals 0. So let's go to the work. And right here I've rewritten our function that we're going to be minimizing and our constraint. And as a Lagrange multiplier problem, the first thing we need to do is take the gradient of f of x, y, and z and g of x, y, and z. G being what we'll call our constraint function. So when you take the partial with respect to x, I, partial with respect to y, j, partial with respect to z, k, and then you do the same thing for the constraint function, and that ends up being even easier because the partials are all 1, so 1 times I is I, times j is j, 1 times k is k. Once you have your gradient functions, what you do is use the equation we were given in class, that the gradient of the function we're trying to minimize is equal to the Lagrange multiplier times the gradient of the constraint function. So if we plug our equations in, or our gradients into that function, we get this equation. And we can distribute our lambdas, and we can separate them into 3 individual equations, setting the I components, the j components, and the k components equal to each other. So that gives us that x, or 2x equals lambda, 2y equals lambda, and 2z equals lambda. Typically, at this point, we're supposed to solve one of these for lambda, but clearly, all 3 of them are equal to lambda. So we can take all 3 of those equations and say, since each one of those is an expression or an equation equaling lambda, we can set 2x, 2y, and 2z equal to each other. And we can divide out the 2 and find out that x equals y equals z. At this point, we need to go back and look at our constraint. This was our constraint function. So we know that x equals y equals z. So we can plug in x in place of y and z in this function, and then carry through algebraically, combining our like terms, adding 9 to both sides, dividing by 3, and we ultimately arrive at x equals 3. Then, if you recall, up here we said x equals y equals z. So if x equals 3, then y and z also equal 3, which gives us our Lagrange point of 3, 3, 3. So we can take that Lagrange point and plug it into our original function, which said x squared plus y squared plus z squared. So 3 squared plus 3 squared plus 3 squared is 9 plus 9 plus 9, which gives us 27. At this point, technically the problem is done according to the book, but Professor Seeberger pointed out to us that the book gives us extra information telling us to minimize or maximize a function, and we're not always given in the examples we have in class whether we have a maximum or minimum, and we need to discover that. So we can take this a step further, and we can, we can test some points. So we do that by, having a little technical difficulty here. Here we go. We test some nearby coordinates. So let's assume we have an x and a y that's fairly close to our 3. So I picked 2.5 and 2.5. Then we can plug those into our constraints. We could take our constraint equation, plug in that value of x and y, and solve, simplifying along the way, and find out that z equals 4. Given that we've picked an x and a y, and we now have a z, we can take and plug those into our original, over here, our original minimizing, or our minimum, our original function of f, x squared plus y squared plus z squared. So we can take our x, y, and z and square them, add them together, and we get 28.5, which is greater than our original 27 that we got when we plugged in 3, 3, and 3. And we should always take a point on the other side. I know it's three-dimensional, so side is probably not the correct way to describe it, but in another region near the near our point 333. So this time I chose x equals 3.5 and y equals 3.5. Again, we plug those into the constraint equation and simplify and continue to simplify, and we arrive at z equals 2. We can then take that point, the x, the y, and the z, the 3.5, 3.5, and 2, and plug that into our original f of x, y, z function, and that yields, again, 28.5, which again is greater than 27. So at that point, even though we knew we had a minimum, we've now shown we've had a minimum because it's smaller than points that are relatively close. So we can say f of x, y, z has a relative minimum of 27 at 3, 3, 3, subject to the given constraint. Thanks. I hope that was helpful.